Thank you, Irfan. I have the pleasure of introducing Stefan Boresch as our first speaker for the last session. He's from the University of Vienna Department of Computational Biological Chemistry, and he'll be talking to us today about transformato.
So thank you for the kind introduction, and I want to start to congratulate the organizers for throwing a great meeting, and of course, thank you for giving me the opportunity to present here. So it's a pleasure to be here and to see how far that field has come. I carried out my first alchemical free energy simulation in 1991, and I can attest it has been a roller coaster ride. And even if we look back, say, 10 years, FEP Plus had not been published. Maybe it was available to selected customers. But more importantly, I think 10 years ago, most of pharmaceutical industry was ready to give up on alchemical free energy methods for good. They were considered too slow, too inaccurate, too brittle. Now, since I have been around for quite some time, you may ask, what was I doing then? And I would actually go back to 2010, and the following two cartoons reflect my assessment from 2010. Maybe just for explanation, PERT is the free energy module in CHARM. And in a sense, the story starts there, because I got a deep distaste for how the free energy part interacts with the underlying MD. And so I got this sort of weird notion, maybe can I avoid it? And this eventually led to transformato, a tool I briefly want to describe here, but more importantly, I want to convey the two sort of underlying ideas, concepts that made this possible. So let's start with speed. In 2010, I wanted to carry out absolute solvation free energies, and actually these can be set up in CHARM very easily, but I quickly realized once I did this, the simulation would slow down by a factor of 3 compared to plain MD of the same system. So I could have lived with that, but at the same time I was benchmarking the first GPU accelerated MD codes. And of course, this was a revelation how fast you could do MD, but of course the codes at the time had no clue about alchemical free energies. So I thought, can I somehow get that job done without free energy specific codes? And if we think about the problem of absolute solvation free energies, I think most of you will say we need soft cores. So suppose we have the charges turned to 0, then the soft cores basically smoothly let the Lennard-Jones go away. Now, and this was maybe a lucky coincidence, just a few years earlier, I had discovered Bennett's acceptance ratio method for myself. I'd been using thermodynamic integration till then, and one test case that convinced me was I basically could take almost any Lennard-Jones sphere in a box of water and annihilate that in one step. No intermediate steps necessary, no soft cores. And this gives me the idea, well, let's turn off 1 or 2 Lennard-Jones instantaneously, use Bennett to get the free energy difference between these two states, and then sort of continue doing this, and we end up at the same end state. So we tried this out, and maybe almost to my surprise as well, it worked quite well. So we wrote a neat little paper, which we call serial atom insertion. And maybe indeed some of the numbers in that paper were obtained with ACE-MD, one early GPU accelerated MD code, which had no alchemical capabilities at all. But with sort of the framework, we sort of could use this. Of course, this only works for absolute solvation free energies, so this is kind of limited. And of course, even more importantly, it's not trivial to set these things up, so it does not help with the brittleness aspect. So let's turn to that one next. And I really am interested in a small poll for the audience here. How many of you could still set up an alchemical transformation from, say, ethane to methanol with just the basic program, charm, amber, bromox, whatever you're used to, but without any of the front-end tooling that you have. Okay, still, let's say 50%. Of course, it may be a skill that will be soon as useful or useless as being able to calculate square roots with paper and pencil. But the problem is, once you get over the learning curve for that, it's still a skill that's extremely program dependent. So if I teach you how to use PERT in charm and you know all this, and then you go off to a group that uses Ember, basically all of that knowledge is useless, or say 2/3. A corollary of this is that there are certain alchemical transformations that are easy, say, with charm, but difficult, say, with Gromax. And another set that's easy to do with Amber, but very difficult with charm. And now, of course, also during the past 10 years, we have seen a lot of user-friendly front ends that take away a lot of the pain, and I'm grateful for them, but they still have specific backends. And in a sense, this hides this complexity or these potential pitfalls from the unsuspecting user. And just during the past year, I've seen some issues from expert users that have run into exactly these problems when they switch their backend with one of these front-end tools. So, as I said, I have started to distrust the built-in free energy capabilities of the programs. So, in a sense, I was staring for a long time at a picture like this. So, methanol and ethane, our little zeroth order benchmark test case. And could I somehow salvage this idea from serial atom insertion? Well, in a sense, of course, I can turn off this hydroxyl group. I can turn off this methyl group. And then I have something that sort of has commonalities. But of course, now I was literally stuck. How do I connect these two things? Obviously, I somehow have to connect these two states to go from here to here. And you see, I mean, we are talking about dummy atoms, but we have a different number of dummy atoms, and this was actually one of my motivations to really understand dummy atoms a little bit better. And so we ended up researching and writing probably my nerdiest paper ever. And the only thing I want to say here, this really convinced me that if we treat dummy atoms correctly, then their contribution must and will cancel exactly from double free energy differences. So my stumbling block of the previous slide just went away, because I know, I mean, I have to do this in a gas phase in an aqueous solution, and the contributions from these guys must cancel exactly. So I don't have to worry about them. So let's take this idea, let's look at this a little bit more in detail. Suppose I want to alchemically transform this guy into that one. So in single topology, we have to decorate both end stands with suitable dummy atoms. I leave it to your imagination what you have to do in your hybrid or dual topology approach to set this up. But given what I just showed on the last slide, why not start with the real physical molecules and, in a sense, turn off the superfluous atoms till we reach sort of a physical common core, as we call it, that is identical between those two. Actually, it's a trick part. So the different numbers of dummy atoms is irrelevant. But still, coming from the left and coming from the right, some of the force field parameters in this common core may be different. So that, of course, we have to take care of to make sure that in the end they're really equivalent. But this is now, again, relatively easy to accomplish because now we have a clear one-to-one correspondence between atoms. And also, please note, we now actually can carry out this alchemical transformation from L1 and L2 without dummy atoms at the end states. They're there, but they are in the interior. So if we take this now to one of our usual cycles, we, instead of going from L1 to L2 directly, we muted L1 to its common core, L2 to its common core, and then combine the two half steps. And in a sense, looking for common cores is what you have to do in looking for transformation networks anyways. So it's very related what we have to do anyways. So how do we now, in an automated manner, carry out the necessary transformations towards these common cores? So this is part of a real molecule we were looking at. So the orange ones we want to transform into dummy atoms. Anything that's green remains to stay. So we basically set up a few simulations in which the charge is gradually scaled to 0. Any residual net charge, I mean, this will not have a net charge of 0, is sort of redistributed around the green atoms. Then we use serial atom insertion to knock out the Lennard-Jones, typically one heavy atom at a time. Hydrogen you can do all at once. And then this is only needed for one of the ligands. This is where we really make sure that the common core resulting from ligand 1 is identical to the one coming from ligand 2. How does this fit in the bigger workflow? So obviously we start with protein and ligand. In our workflow, we use charm GUI to set up the systems in complex and free form. Actually, we don't load up every ligand to charm GUI. We wrote a little bit of tooling. If you know charm GUI, you get all the scripts to do the work. And if you have a sort of similar series of ligands, then you basically take one set of template scripts and rerun them over all the other ligands. And so this is what this little tool automates a little bit. Only then transformato comes in a sense, now compares the two structures, the PSFs in charm language, and looks for the common core and devises the necessary transformation steps to turn off the superfluous atoms. Now, each of these intermediate states is a fully self-contained input for plain MD, which we then run, and we currently support OpenMM and charm. So we write trajectories. These have to be post-processed to get the input for mbar. The post-processing is also completely automated by transformato, and we use PyMBar for the last step. So that's a relatively automated workflow that easily extends to several ligands. Now, of course, we have to show and prove that this actually works. And I was very intrigued seeing this benchmark set. David was, for example, involved from 2018, because this is exactly what I was looking for, because I have at least what I color him here in blue is the common cores that we used. And so we started out with relative solvation free energies. And I have an extra slide, but in the sake of time, I hope you believe me that we really relatively rigorously checked that we get the same results with a plain PERT with regular free energy tooling and with our approach. So we convinced ourselves that this works. Then, in a sense, it was easy to go to relative binding free energies. So we looked at a few of the usual suspects. So one case where we do poorly, I think it's fair to blame the force field, because there were PMX results available also with CGNFF, and they are relatively close to what we are getting. And then, of course, in a sort of full circle, I said, well, wait a second, if we go to a 0 common core, then we are back to absolute. So at least for absolute solvation free energies, that's easy. And so this is what we most recently did, basically applying our toolkit to almost all of the FreeSolve database. And to the best of my knowledge, that's the first set of data for the charm force field. So at this point, where do we stand? So this little tool is available at GitHub. And I showed you examples of relative and absolute solvation free energies and relative binding free energies. Of course, now the two caveats. This obviously works best for congeneric series of ligands, and initially we are relatively tied to the charm force field family. So that's where I'm coming from. Now, and this is the biggest limitation, it's not well suited if there is no or just a very small common core, and we have not tackled the issue of trying to do ring breaking information in this type of setting. But at that point, I think maybe if you run into these issues, then really go absolute, and I hope you trust me that I know how to add restraints. We have in-house from a neighboring department that had a problem, and they wanted to use the amber force field, so we have started dealing with this, and we also in experimental versions can do changes not only to the ligand, but also do minor modifications to the receptor. We have no provisions for charge changes at the moment, but that should be easy to add, having this counteracting charge. But I don't want to dwell on this. You may ask, why do all the trouble? So my initial goal was to separate the alchemy from running the MD. And this takes care of the speed issue. That's good, but we actually gain something else. We can utilize any feature of the underlying MD program to the fullest. And let me show you some examples. So one of the things we noted, the CHARM small molecule force field for quite some time now uses lone pairs of center charges. And this gives a lot of other programs quite headaches. And we also had a headache because we are using PARMET to manipulate PSFs, and PARMET had some issues with that, which we initially worked around and I think submitted a bug fix. But nothing stopped us using lone pairs and use the CHARM generalized force field as is. So the absolute solvation free energies I showed, we added an isotropic long-range correction. But then I said, wait, that's stupid. I just learned from the CHARM membrane force field people we need to go to Lennard-Jones PME. CHARM supports it, OpenMM supports it. Why not use it? So this was just needed one change in one line of the OpenMM input template code, and we tested this on a number of compounds from the solvation. We literally get the same results with Lennard-Jones PME as with the isotropic long-range correction. And if used correctly, this can actually make the simulation run faster. I have a master student who is now looking into adopting this for the Drude force field. I don't have sufficient data to show yet, but I've seen enough results to be convinced that this will work more or less out of the box. And I'm not sure, I hope you visited Sarah's poster. We are working quite a lot of trying to actually then correct our results to either QMMM or machine learn MM potentials. And of course, this is a sort of nice workflow which this fits in together. So this was about separating alchemy from the underlying MD. But I think this separation into steps has some other advantages. I really think system setup preparation is not necessarily the job of the free energy program. So as I say, we are using CHARM GUI. It should be relatively easy to replace this by some other tooling, but I like CHARM GUI. And so basically any system CHARM GUI can handle, we could run alchemical simulations, and CHARM GUI can handle quite a bit. And in terms of the alchemy itself, again, I want to point out that we now can do relative transformations without end states. And since we're only transforming physical atoms into dummy atoms, this is actually very easy to automate. And as I said, I very much believe, and so I would push for that direction, that we actually use the best tooling for each step task of a full free energy workflow. And if you're looking for something minimalistic, then please give transformato a try. And now with this, I couldn't have done this without the help of two people. Markus, over there, really did the heavy lifting, and then Johannes took over and fixed lots and lots of little paper cuts to make this usable, so that we actually could have rotation students in the group without any experience use this. Benedict, Joseph, and Alexander made some important contributions to the code. Marvin is looking at the Drude work now. Asmund has been doing this little tooling to automate or avoid having to send up everything to CHARM GUI and sources of funding. With this, thank you for your attention, and I'm hoping
Yeah, thanks. Great talk, Stefan. Now, if I understand the idea of the serial atom insertion, right, does that mean that translates into maybe a lambda schedule with more stage? And how do you deal with maybe long correlation time? Or, do you think are you running more shorter simulation and then taking the output of one trajectory, feeding it into the next, or everything in parallel?
We run everything in parallel, of course, as you say. So I should have pointed this out. We don't have lambda anymore. We have really discrete intermediate steps.
Mm-hmm.
And of course, with serial atom insertion, this very much depends on the size, how many atoms you have to turn off. As I say, hydrogens you can do basically all at once, at least in charm force field. I don't know, maybe in other force fields that might be trickier. Then a safe protocol is one heavy atom at a time, and maybe in the absolute case, do a little intermediate step for the very last one. That always is a little bit trickier, but then we run each of these states in parallel, or at least independently. And so, no, we don't really seem to see big correlation problems. And I think that you need more states for bigger systems actually might make sense, because if you have one of these usual 20 lambdas for everything, then it's total overkill for small things. And then if you have some, whatever, 100 atom ligand, then that's probably not enough.
Okay, thanks.
There was one.
Stefan, a very elegant way to set up transformations. In the context of relative binding free energies, I'm wondering if you're committing yourself to something like a maximum common substructure intermediate, wouldn't that be one that usually binds extremely badly and maybe is not very stable in MD simulations?
So this is a worry I do indeed have. We have some experimental code to add restraints at just really making sure this doesn't fly away. I should say we checked all our test systems where we use this and didn't see any problems, but which does not mean that it may not arise. So it's something we are well aware of. Thank you.
One more question?
Thank you, great talk. Because your dummies have bonded interactions always on, do you have to do something special at the middle where you have different dummies on one side and different dummies at the other?
So in this one paper I briefly had, I think we have recipes, and the way you end up in these type of applications correspond to what we call the terminal junction. And there in fact, we leave everything on, but because if it's a terminal junction, any side effects will be small. If we want to really be puristic and stick to my own rules, then you just need to turn off some dihedrals and no angles. There are some typical some dihedrals, so any effects are really, really small there.
Thank you, Stefan. Can we get one more round of applause for him?